Unit 4, waves. Now we're going to do the last section, which is wave properties, which will last for 2 hours in class. In this section, we will look at 4 aspects, 4 properties of waves: reflection, refraction, diffraction, and interference. The syllabus says that we describe the reflection and transmission of waves at a boundary between 2 media. So when a wave reaches a boundary, 2 things will happen. Some of the wave will be transmitted, some will be reflected. Transmitted means it goes through the boundary to the second medium. Some is reflected and stays inside the first medium. The more different the media, or rather there's this characteristic called a refractive index. The more difference, the greater the difference in the refractive index, the stronger the reflection, the less will be transmitted, the more will be reflected. So we will look at the refractive index of the medium. Here's some examples. Because of the difference in refractive index, we get refractions between air and water. Here's some examples. Okay, this is the refractive index between air and glass. Light is reflected off the glass and off the metal because there's a great difference in refractive index between the air and the glass, or air and the metal. Another example is between the air and the water. The light reflects off the water. Some is refracted, but not a great deal is reflected due to the difference in refractive index. Here's another example. At a very large angle, you see a great deal of the light which is incident on the water, surface of the water. A great deal of that light is reflected. Not very much will be refracted at this angle. There's a demonstration where we can show what happens when light goes through oil and goes through Pyrex, and their refractive indices are very close together. So there's an interesting demonstration there. Okay, what happens with the reflection of a single pulse? You have to know what happens to the wave on a string. The wave travels. Okay, yes. The wave travels from left to right. From left to right, the disturbance is above the equilibrium position. When it hits the wave, then it's fixed at this point. When it hits the wave, what happens? It comes back on the other side of the string. So we have a negative displacement there. So the wave is inverted. The reason for that is basically because as the wave comes in to this fixed point, the node, the point where it's tied, pulls down on the wave, and afterwards it will keep on pulling down. So due to Newton's third law, the node will pull the wave down because the wave is pulling up on the node, which will be here, and when it reflects, it will be on the other side. At Snell's law, this is to do with a set of ratios: the refractive index in terms of the ratio of the speeds of the wave in the 2 media, and also in terms of the angles of the instance and refraction, and also the wavelength, even though it's not mentioned here. We have 2 ways of looking at refractive index. This is the refractive index of media 1, which is the air, the refractive index of media 2, which is the glass. Now, the refractive index of air is more or less 1. So when we're talking about ratios, when we have 1 divided by another number, we're just thinking of the second number. So sometimes we just talk about the refractive index of the second medium relative to air, or relative to vacuum. If we have if you do have 2 media which are not air or vacuum, then N1 and N2 are important. But for now, N1 is going to be 1, so it makes it very straightforward. The light comes in at a certain angle, it gets refracted, it gets bent, it slows down. If you notice that, do that again. As it comes in, it goes quickly, then it slows down in the second medium. This represents quite well what happens. We draw a normal, which is a line at right angles to the surface where the incident light hits the glass. We define this as the angle of an incidence, the angle between the ray, the incident ray, and the normal, and we define this as the refractive index, the angle between the refracted ray and the normal. So what happens? A, it slows down. It bends towards the normal. It means that the incident angle is greater than the refractive angle. N is the refractive index of the second medium, in other words N2, this is N1 if we're talking about air. And there's this, another ratio that we're interested in, which is the sine of this angle divided by the sine of that angle will be greater than 1, because this is a greater angle than this angle. Or more specifically, the sine of the incident angle divided by the sine of the refracted angle will be equal to N2, which is the refractive index of the second medium, divided by the refractive index of the first medium. Notice that they're inverted. Here we go. The sine of this angle divided by the sine of that angle is equal to the refractive index of the second medium divided by the refractive index of the first medium. As I said, in most cases where we're talking about air or vacuum, so N1 is equal to 1. So this becomes 1. So we have sine of the angle of incidence divided by the sine of the angle of refraction will basically be equal to the refractive index of the second medium, because this is 1. Here's an example. The refractive index of air is 1. The refractive index of glass, in this glass, is 2. The angle of incidence is 45. What would the angle of refraction be? I suggest you pause. And the solution is as follows. The ratio of the sines, we need to find is the refracted angle, the angle of refraction. This is 1, so we just need to rearrange that to get a value in there. So what I did here was I flipped this, so we basically multiply 1 over 1.52 times by the sine of 45, and then inverse sine to get the second angle. Oops. Okay. Sometimes the light is going from glass to air, in which case it bends away from the normal, because it travels faster in air than it does in glass or water. This is another way of representing that ratio. We have to look at refraction in one dimension. The light wave is hitting the slow medium. First of all, the wave fronts come in. This is the ray goes into the second medium. You can't see any diversion because it comes along the normal. These are the wave fronts. You should notice that they have a large wavelength when it's approaching, and when it gets into the medium, the second medium, the wavelength gets smaller because the speed changes. This is the first refractive index of the first medium, refractive index of the second medium. So what the rules are, the frequency is still the same, it remains unchanged. We know that V is equal to F lambda. We rearrange to have F is equal to V over lambda. So F for the first medium is equal to V1 over lambda 1 is equal to F for the second medium, V2 over lambda 2. We rearrange, so the ratio of the velocities is equal to the ratio of the wavelengths. But this is a large wavelength, it has a large velocity. Small wavelength, small velocity. And this is also the ratio of the refractive indices. Notice that this is V1 over V2, lambda 1 over lambda 2, but this is flipped, so it's N2 divided by N1. Here we have the same equation there, V1 divided by V2, lambda 1 divided by lambda 2, N2 divided by N1. This has been flipped, okay, but the sine of the angle is still in the same order as 1, 1, 1. This meters a second, but the refractive indices are swapped out in the equation. Water waves travel from deep water to shallow water. Find the ratio of the speeds. This is a very common question. How do we find the ratio of these speeds? There's no information about speeds, but what we can do is we know that the ratio of the speeds is going to be equal to the ratio of the wavelengths. So you basically, with a ruler, need to measure what one wavelength is here and one wavelength is here. And if you know that, then you can work out the ratio of the speeds. The ratio of the speeds would be equal to the ratio of the wavelengths. It's just a ratio, not the absolute values we're finding. Okay. Yeah. So this is the same thing here. These are the refractive indices of different media. Notice that glass is 1.52. Zircon, whatever that is 1.92. Diamond has got a value for 2.4. Here's a question that I would like you to attempt. This is from Chris Hamper's textbook. So pause and try these 3 questions now.